The NK-33 and NK-43 are rocket engines designed and built in the late 1960s and early 1970s by the Kuznetsov Design Bureau. The NK designation is derived from the initials of chief designer Nikolay Kuznetsov. NK-33 was among the most powerful LOX RP-1 rocket engines when it was built, with a high specific impulse and low structural mass. They were intended for the ill-fated Soviet N-1 rocket moonshot. NK-33 engine is now used on the first stage of the Soyuz 2-1V launch vehicle. Design. The NK-33 series engines are high-pressure, regeneratively cooled staged combustion cycle bipropellant rocket engines, and use oxygen-rich pre-burners to drive the turbopumps. The turbopumps require subcooled liquid oxygen to cool the bearings. These kinds of burners are highly unusual, since the hot oxygen-rich exhaust tends to attack metal, causing burn-through failures. The United States had not investigated oxygen-rich combustion technologies until the Integrated Powerhead Demonstrator project in the early 2000s. The Soviets, however, perfected the metallurgy behind this method. The nozzle was constructed from corrugated metal, brazed to an outer and inner lining, giving a simple, light, but strong structure. In addition, since the NK-33 uses LOX and Rg1 as propellants which have similar densities, a single rotating shaft could be used for both turbopumps. The NK-33 engine is among the highest thrust-to-weight ratio of any Earth-launchable rocket engine. Only NPO Energomash Road 253 and SpaceX Merlin 1D engine achieve a higher ratio. The specific impulse of the NK-33 is significantly higher than both these engines. The NK-43 is similar to the NK-33, but is designed for an upper stage, not a first stage. It has a longer nozzle, optimized for operation at altitude, where there is little to no ambient air pressure. This gives it a higher thrust and specific impulse, but makes it longer and heavier. It has a thrust-to-weight ratio of about 120:1. The predecessors of NK-33 and NK-43 are the earlier NK-15 and NK-15V engines, respectively. The oxygen-rich technology lives on in the Road 170-171 engines, the Road 180, and recently developed Road 191 derivatives. But these engines have no direct connection to the NK-33. History. The N-1 launcher originally used NK-15 engines for its first stage, and a high-altitude modification in its second stage. After 4 consecutive launch failures and no successes, the project was cancelled. While other aspects of the vehicle were being modified or redesigned, Kuznetsov improved his contributions into the NK-33 and NK-43, respectively. The second-generation vehicle was to be called the N-1F. By this point the moon race was long lost, and the Soviet space program was looking to the Energy as its heavy launcher. No N-1F ever reached the launch pad. When the N-1 program was shut down, all work on the project was ordered destroyed. A bureaucrat instead took the engines, worth millions of dollars each, and stored them in a warehouse. Word of the engines eventually spread to America. Nearly 30 years after they were built, disbelieving rocket engineers were led to the warehouse. One of the engines was later taken to America, and the precise specification of the engine was demonstrated on a test stand. Combustion chamber design. About 60 engines survived in the forest of engines, as described by engineers on a trip to the warehouse. In the mid-1990s, Russia sold 36 engines to Aerojet General for $1.1 million each, shipping them to the company facility in Sacramento, California. During the engine test in Sacramento, the engine hit its specifications. Aerojet now had the proof they needed to sell the engines for the latest launch of satellites. The NK-33 closed-cycle technology works by sending the auxiliary engine's exhaust into the main combustion chamber. This made the engine design unique. This technology was believed to be impossible by Western rocket engineers. The fully heated liquid O2 flows through the preburner and into the main chamber. In this design, the extremely hot oxygen-rich mixture made the engine dangerous. It was known to melt 3-inch thick castings, like candle wax. This resulted in Lockheed Martin developing a new metal to handle the heat, combustion and temperature. One of the controversies in the Kremlin over supplying the engine to the US was that the design of the engine was similar to Russian ICBM engine design. The NK-33's design was used in the later RD-180 engine, which were twice the size of the NK-33. The RD-180 engines were used to power Atlas rockets. This is one of the first engines produced in America using the NK-33's closed-cycle technology. This company also acquired a license for the production of new engines. Kistler Aerospace, later called Rocketplane Kistler, designed the K-1 rocket around 3 NK-33s and an NK-43. On August 18, 2006, NASA announced that RPK had been chosen to develop commercial orbital transportation services for the International Space Station. The plan called for demonstration flights between 2008 and 2010. RPK would have received up to $207 million if they met all NASA milestones. But on September 7, 2007, NASA issued a default letter warning that it would terminate the COTS agreement with Rocketplane Kistler in 30 days because RPK had not met several contract milestones. Antares, the initial version of the Orbital Sciences Antares light-to-medium lift launcher, had two modified NK-33 in the first stage, a solid Castor-30-based second stage and an optional solid hypergolic third stage. The NK-33s were imported from Russia to the United States, modified, and redesignated as Aerojet AJ-26s. This involved removing some electrical harnessing, adding U.S. electronics, qualifying it for U.S. propellants, and modifying the steering system. In 2010, stockpiled NK-33 engines were successfully tested for use by the Orbital Sciences Antares light-to-medium lift launcher. The Antares rocket was successfully launched from NASA's Wallops Flight Facility on April 21, 2013. This marked the first successful launch of the NK-33 Heritage engines built in early 1970s. Aerojet agreed to recondition sufficient NK-33s to serve Orbital's 16-flight NASA Commercial Resupply Services contract. Beyond that, it had a stockpile of 23 1960s and 1970s-era engines. Kuznetsov no longer manufactures the engines, so Orbital sought to buy RD-180 engines. Because NPO Energomash's contract with United Launch Alliance prevented this, Orbital sued ULA alleging antitrust violations. Aerojet offered to work with Kuznetsov to restart production of new NK-33 engines to assure Orbital of an ongoing supply. However, manufacturing defects in the engine's liquid oxygen turbopump and design flaws in the hydraulic balance assembly and thrust bearings were proposed as two possible causes of the 2014 Antares launch failure. As announced on 5 November 2014, Orbital decided to drop the AJ-26 first stage from the Antares and source an alternative engine. On December 17, 2014, Orbital Sciences announced that it would use the NPO-181 on second-generation Antares launch vehicles and had contracted directly with NPO for up to 60 Road 181 engines. 2 engines are used on the first stage of the current Antares. On May 13, 2014, Russian Deputy Prime Minister Dmitry Rogozin announced that Russia would no longer supply rocket engines for U.S. military launches, amid tensions arising from the 2014 Russian military intervention in Ukraine. Current and proposed uses. RSC Energia is proposing an Aurora L.SK launch vehicle, which would use an NK-33 to power the first stage and a Block DMSL for the second stage. Soyuz 21V. In the early 2010s, the Soyuz launch vehicle family was retrofitted with the NK-33 engine, using the lower weight and greater efficiency to increase payload. The simpler design and use of surplus hardware might actually reduce cost. TSSKB Progress uses the NK-33 as the first stage engine of the lightweight version of the Soyuz rocket family, the Soyuz 21V. The NK-33 intended for the Soyuz 21V was successfully hot-fired on 15 January 2013, following a series of cold-fire and systems tests of the fully assembled Soyuz 1 in 2011-2012. The NK-33 powered rocket was finally designated Soyuz 21V, with its maiden flight having taken place on 28 December 2013. One NK-33 engine replaces the Soyuz's central Road 108, with the 4 boosters of the first stage omitted. A version of the Soyuz rocket with 4 boosters powered by NK-33 engines is as of 2015 not realized, which results in a reduced payload compared to the Soyuz 2 launch vehicle versions. During the years there have been many versions of this engine. NK-15 initial version for the N1 first stage. NK-15V modified NK-15 optimized for vacuum operation, used on the N1 second stage. NK-33 improved version for the N1F first stage, never flown. NK-43 vacuum-optimized NK-33 for the N1F second stage, never flown. AJ-26-58 and AJ-26-59 modified NK-33 by Aerojet Rocketdyne. Planned used on the Kisler K-1. AJ-26-62 modified NK-33 with additional gimbal mechanism by Aerojet Rocketdyne. Used on the Antares 100 series first stage. NK-33A refurbished NK-33. Used on the Soyuz 21V first stage. NK-33-1 uprated NK-33 with gimbal mechanism. Planned used on the Soyuz 2.3 core stage. Gallery.